Here's your Sioux Falls physics teachers looking today at thermal expansion. We're looking at an aluminum roof. Coefficient of linear expansion is given, and we also have an initial length of the aluminum. We're starting in a winter day at 7 degrees Celsius, and we're looking at a new temperature during the summer of 38 degrees Celsius. It says calculate the new length of each piece of aluminum. So first of all, our linear expansion equation is quite simply the coefficient multiplied times the initial length times the change in temperature. Our coefficient is given as 24 times 10 to the negative 6th, and again that's degrees Celsius to the negative 1st. Our initial length is 0.85 meters, and the change in temperature can be found by comparing the original temperature of 7 degrees to the final temperature of 38 degrees, and we end up with a change of 31 degrees Celsius. Plugging those numbers in, we get a change in length of 6.32 times 10 to the negative 4th meters. Now notice we're actually not done yet. It does say to calculate the new length, and since we're going from low temperature to high temperature, then our new length would be expanded. It would be greater than our original, and so we would take our original of 0.8500, add on our change of 6.3 times 10 to the negative 4th, and we have a new length of 0.8506 meters. Again, notice very, very small change from that change in temperature.
Now we're dealing with an ideal gas. In this question, we're asking what is the temperature of 5 moles in an ideal gas that has a pressure of 2 atmospheres and a volume of 3 meters cubed. So the first thing you should pop into your head is an equation that just stands for ideal gas, and that is PV equals nRT. Now, we know what the volume is. We know what the number of moles N are. We know what the pressure is, but there's a problem with our pressure. We either have to be in liters, and then for volume and atmospheres, or we have to be in pascals and meters cubed. So let's convert 2 atmospheres to pascals. To do that, we know that 1 atmosphere is equal to 101,300 pascals. So 2 atmospheres will be 202,600 pascals. Knowing that, we can just go ahead and start plugging in that problem. So we've got 202,600 pascals. We've got a volume of 3 meters cubed equals N, which is 5. Now we have to choose which R we're going to use. Because we're using this one, we're going to use the value of R being 8.31. Had we used liters, we would have had to use the other value of R, equals times temperature. Now it's just a simple problem of solving. Once we do the math, we're going to come up with a temperature of 14,628 degrees Kelvin.
Okay, another problem here on ideal gas. Temperature of a given amount of substance is constant. We're going to calculate the new volume of a balloon if the pressure increases. So given that the pressure multiplied by the volume is equal to nRT, and since the temperature is staying constant, we know that the pressure times the volume that I start with has to equal the pressure times the volume that I end with. So just plugging in here, our initial pressure of the balloon is 100,000 pascals of pressure. The volume of that balloon to start with is 4 cubic meters. That is going to equal the new pressure, which is 300,000, and we want to find this new volume. So solving for the new volume, we get a new volume of 1.33 cubic meters, which, if we stop and think about it, if the pressure on the balloon increases, we would expect that the volume of that balloon should go down as a result of that.
Okay, welcome back again. We're going to look at another ideal gas problem now. If the volume of a glass container stays the same, calculate the new temperature of an ideal gas if the pressure increases from 100,000 pascals to 300 pascals for 2 moles of a substance at 300 degrees Kelvin. Once again, if you're looking at ideal gas, the equation that should pop into your head is the ideal gas equation. PV equals nRT. If we're comparing things from before and after, we should look first to see what is not changing. Well, one of the things that's not changing is the number of moles. They're not going to change. The other thing that's not going to change is the volume. It's very hard to change the volume of a glass container. So if we rearrange our equation so that all the constant values, the values not changing, are on the same side, we end up by dividing by n and r and dividing by p. When we do that, we end up with T over P equals V over N times R. Now, since the V over N times R is constant, that means that our temperature we start with over our pressure we start with has to equal our temperature we finish with over the pressure we finish with. At this point, all we got to do is plug in the values. So, looking at this problem, we know that our starting temperature is 300 Kelvin, and you've got to always be in Kelvin whenever you're using this, divided by our pressure that we started with, which was 100,000 pascals, roughly 1 atmosphere. That has to equal our temperature that we finish with, which is what we're looking for, divided by our pressure that we finish with, which is 300,000 pascals. Solving for T, we come up with a final temperature of 900 degrees Kelvin.
Hey everyone, Sioux Falls physics teachers here, looking today at kinetic energy and velocity of an ideal gas. First we're going to calculate the kinetic energy of 1 mole of helium gas. And again, remember that our kinetic energy equation is simply 3/2 times the constant, and because we're dealing with 1 mole, here we will put our constant R times the temperature. And again, our constant R is 8.31 joules per mole Kelvin times our temperature of 400 Kelvin. Notice that what we're going to end up with is the kelvins will cancel out, and we will be ending up with an answer in joules per mole. And if we calculate those all out, we end up with a kinetic energy of 4,990 joules. Okay, now the second half of this is to calculate the RMS velocity. And again, there's a couple of different equations that we could use. Because we're dealing with a mole here, the version that is going to be the most efficient for us is 3 times our gas constant R times the temperature divided by the mass. And again, remember that these two things here really need to match. If we're using the gas constant per mole, then we also want the mass per mole, and so we use a capital M to show that. Now, in our information, it reminds us that for helium, our mass is 4.0026 grams per mole. In doing this equation, however, we will need that in kilograms. So as we write this out, we will be using 3 times 8.31 times our temperature of 400 Kelvin, and then divided by our mass, which in this case is going to be 4.0026 times 10 to the negative third, because that will